So, for example, if we have a molecule, we excite from a specific initial state to a specific final state, and we collect all of the initial, all of the, so in the excited state, it may have the lift quench or collisional transfer. So if you read my notes, that talks about the extension of the physical system, and in certain limits, we recover the state of the Q. And if you read it carefully, you'll see the Q is the quench rate out of the emission that you collect. If you decide to collect the emission from a spectral region that encompasses all of the possible emission wavelengths from that state. So say you come to an excited state. Time zero, you can emit, be quenched, or go to another state. That's the diagram for that. Once you're there, you have the same choices. Emit, quench, transfer. Emit, quench, transfer. And in the limit, those A's and Q's are all the same number. We'll end up with A over Q comes back to the two-level model. Within the weak excitation limit in the range of parameters that we're talking about. The good news is the two-level model still applies in the weak excitation. So it's actually a nice thing. We don't necessarily know yet what Q is, but we're still in the same formula. Good. Any other questions? So now we're going to move on to some examples, some applications. In this lecture 14, we're going to do small molecules, and then in lecture 15, we're going to end up on big molecules, flow tracers. So we're now imagining that we're doing planar laser fluorescence. We shed our light into a sheet of light. It might be 0.5 millimeter thick, it might be 4 or 5 centimeters high, it might be bigger. And we're going to talk about some applications now. It looks like I'm going to start with OH PLIF and maybe move into the infrared, hypersonic flows, some challenges and reactions. So basically going to move all the way to hypersonic flows. COCO. So imagine this is some sort of a picture. This would be a picture of a forced jet. So some sort of a jet is being forced at some frequency, and this jet fluid is mixing with the ambient, and we're measuring in this false color display the mole fraction of the jet. That's what I like to do. So this is two-dimensional imaging using typically what I'll call a digital camera. So excitation lasers formed into a sheet with usually 2 optical elements. This is the 1D LIF, this is the 2D LIF. This, of course, could be a camera that's sensitive in the UV, the visible, the infrared. The cameras are different. The filters are different, but it's possible to have infrared cameras that corresponds to this picture I'm going to show you. Or it could be a UV sensitive camera. In the case of usually the output image for is the detectors are sensitive in the visible. So if the light is in the UV, you have to go through a stage in which you convert the UV photons into electrons, which then produce a visible image. So there's stages in these cameras to convert the wavelengths that you have into finally the false color display of the signal. Okay, so typically, if we're going to do PLIF, we use a pulse laser in order to achieve a high flux rate of photons. So basically, you would turn the camera on and off. So turn the camera on, collect the light only for a few microseconds, perhaps, and then off. So you don't collect light in between the laser pulses. The idea is that these times are so short that you effectively freeze the flow field, and that is true unless it's really high-speed flow. These cameras will not have the same high performance as a photomultiplier, but it's good. You can do some averaging depending upon what the experiment is. If the flow is steady or not, you can average. So basically, could be CW laser, could be pulsed, usually pulsed, could be unsteady, could be steady, depends. Lots of possibilities. For a while, we actually did 3D. I had a student, we did this. We had a laser which had a pulse length of, instead of 10 nanoseconds, had a pulse length, I think, of a few microseconds. What we did, instead of having just this sheet fixed, is we had a spinning mirror here so that illumination plane would scan rapidly with time, and then this camera, which is fixed, would collect light at different instants in time corresponding to different orientations of this illumination plane. And from this, we could get a 3D image. So a 3D image in the sense that we have to acquire them all in a time short to fluid motion. And each of these planes is from a different orientation. So that was pretty successful. This means that we have to cross the flow field in the time, in the length of time of the laser pulse, which for us was, I think, a few microseconds. That's unusual. Most lasers have short pulse lengths. And you have to think about the depth of field of the lens and so on. We actually did this also did this for a cube display, where we actually had a forced flame and we could collect these images over a period of time at instance of the fluctuations in the flow, and that produced various kinds of movies. So we actually had, I don't know if I'm going to show you, can't remember now. We would build a cube of data at a fixed phase, which means a fixed time, and then we could have, with that cube of data, we could interrogate it from any angle, and then at various times, and we could get 4D displays. So that turned out to be, we had so much data that I had a friend who worked for Pixar, and we got one of their Pixar computers to process all these data. That was back in a time when computers weren't so powerful as they are now. Okay, what if we want to measure density? What are the things we want to measure? Density, meaning the number density of that species in an absorbing state. Let's say that's most often what you're after. How do you measure the number density of that species? Now that's proportional to the number density of the species times the Boltzmann fraction divided by Q, where Q is the quench rate. So in the limit of weak excitation, that is linear excitation, where A is smaller than Q, and A is known, and omega over 4 pi is known, and the volume and laser intensity in B are known, that just says the signal is proportional to the number density of the species and a Boltzmann fraction. So the product of number density of the species and the Boltzmann fraction is what's giving me N10 divided by Q. So that's a common situation. So we assume we know most of these things. We know that A and B, and we know by measurement typically these numbers. Sometimes this is done by what's called Rayleigh scattering. So we do an experiment, and we have a plane of light, and we know the power in, and if you look at the equations for Rayleigh scattering, they're also in terms of the same unknowns that we're after of intensity and angle. You can then use a Rayleigh scattering method where you fix the number density and you measure the laser line width and these other quantities that are the same in the Rayleigh scattering measurement as in the fluorescence. So there's a way to calibrate essentially everything except what remains. Now the signal is proportional to some constants times the number density of this species, where this constant contains all of these things if we know the Boltzmann fraction and Q. We have to have some sort of calibration for those two, or we have to know the temperature. If the temperature is varying, we have a bit of a problem, and we have to also measure T. Or what about picking a quantum state for which the temperature dependence of F and Q cancels? So that's a trick. We play that trick once in a while. So if you're after the mole fraction, we can write this now in terms of the number. Remember, we have all the constants except the number density of the species and the Boltzmann fraction, which depends upon T. So if you know T, okay, but if you don't know T. But we can write this Q as a collision frequency, even though we do not yet know the cross-section. And when you do that, you can show that the signal in photons per second, it is proportional to some constants and the mole fraction. So if you pick the right quantum state, you can nullify all these temperature dependencies and get a signal proportional to the mole fraction you're after. Well, this isn't perfect, but it's pretty good. So this is one way to try to get images that are proportional to the mole fraction, if that's what you're after. So you have to select a quantum transition, which depends upon V and J, such that this is independent of T. And you can do this over some narrow temperature range. Now, there's another strategy, and that is, well, let's do this the other way around. What if we have a signal that's proportional to the mole fraction and this temperature-dependent quantity? Instead of making this independent of temperature, why not fix this T and select V and J so that it depends on T? That was, in fact, I think, the very first PLIF image of temperature in a flame that we did this trick. And we imaged, I think it was around 1985, 86. We imaged temperature in a flame by fixing the mole fraction of nitric oxide at some number like 300 parts per million. So if you fix the mole fraction, pick a strongly temperature-dependent quantum state, you could get a signal that's proportional to, dependent on T. The alternative method that's used to get temperature, since temperature is so important, is to take the ratio of signals for different transitions 1 and 2, which have different quantum populations, but they depend both on the number density of that species. So the species dependence drops out, and you're left with a function of T. And that's a good strategy. That means we don't have to fix the mole fractions. You have to make some approximations, the assumptions that the Q's are independent of transition, but that's pretty good. So this is a good way. What's the downside of this? The downside is anytime you take a ratio, you have more trouble with noise, getting the absolute ratio, constant laser intensities, things like that. So, but still, it's the most sensitive way to measure temperature. Okay, that's just telling you there's a way to get temperature, and there's a way to get number density, and there's a way to get mole fraction. You usually need to know temperature first to make a quantitative mole fraction. I want to give you the history of PLAF. The first PLF was around 1982. That was this picture here that we did, I showed you a minute ago. We then did this in a turbulent flame at General Electric in New York, about 1984. That was on the cover of Science. We did this 3D cube. Oh, here's a picture of this. So we did a cube of data. So this is a cube at a particular phasing of this forced jet. So by repetitively forcing the jet, we could take observations at different planes at a given point in that phase or time, and we could get this cube of data that you could analyze from any angle, which was kind of interesting. That's when we had to get a computer from Pixar. Along about 1982 is when we realized that we needed to talk to our fluid mechanics friends. That's when we developed acetone. We then began to work in scramjet problems. I think I'm going to talk about this some more. This is a jet of hydrogen fuel into a cross flow of high temperature air. And we're seeing the burning jet, the penetration of the jet and the burning of the jet. These were images of temperature. This is the case where the cross flow and the jet were both seeded with nitric oxide. Here's the case where we only seed the jet. So you can see where the fuel is, hydrogen fuel seeded with nitric oxide, about 500 parts per million. And so we can measure the temperature of the jet independent of the. There were times also when we looked at supersonic flows. This is an underexpanded jet here in which you have, you'll recognize the barrel shock if you've had a course in gas dynamics. And we illuminated from different angles, and we were able to measure temperature and even velocities from that case. So that was about 1996 or so. What's happened since then is that we've seen a kind of explosion of people using PLIF, especially with tracers, to look at mixing of fuel jets in industrial laboratories. Where is it today? The real trend is to use really high-speed PLIF, kilohertz rate PLIF. So you can look at transients and dynamics of combustors, for example, swirl combustors. What's the problem? Well, you need a laser that can pulse at kilohertz rates, which means it's not the usual YAG laser. What happens to the energy per pulse? The signals depend on the energy in the pulse. So when you start going at kilohertz rates, you usually have lower energy per pulse, and so it's hard to achieve high signal noise ratios when you go at kilohertz rates. But still, that is the trend. Higher and higher pulse rates with the lasers. And what happens is people will do what's called a burst pulse laser, in which you have, you take your laser and you take the energy and you confine it to, say, 100 pulses. So you try to get more energy per pulse by letting it only run for, say, 100 pulses. Okay, now I want to go to tracer-based flip. So this was Jerry Seisman at Georgia Tech. So there's people here from Georgia Tech, maybe. Anybody from Georgia Tech here? Should have been. Okay. So this is my student, Jerry Seisman, professor at Georgia Tech. And he did this back around 1990. So it's interesting. Here we are quite a bit later. And it's amazing. The images obtained now are not a whole lot better than the ones that Jerry Seisman took. So basically, some sort of a, this was a methane air piloted flame burner. We're burning hydrogen, say. This would be a flame. The laser was a tunable xenon chloride laser. So xenon chloride is one of the exomerate glass mixtures that you can have. It happens that laser emits light at a wavelength that's absorbed by OH. So you can do pictures of OH this way. And we got about 100 millijoules at, it looks like, I can't read that, maybe 60 hertz. Formed into a sheet, and we're going to do this at high speed. Now you can illuminate the plane in the vertical direction, or you can put it in the horizontal direction. I'll show you. So this gives you an axial cross-section or a radial cross-section. These are the pictures that he took back in that period in time. This is a 2 millimeter diameter jet, OH PLIF. Now, these are false color displays of the signal intensity. They're proportional to the amount of OH in the absorbing quantum state. We don't know what the temperature is. We don't exactly know what Q is, but the signals are quantitative in time, quantitative in space, but the conversion of the signal to the OH mole fraction is tricky. So sometimes, though, you only want to look at the flame structure. So there's the flame structure. As we increase the Reynolds number to about 50,000. So you get up to higher Reynolds number, the flame starts to lift off. You start getting these broadened regions. So looking closer to laminar here, gradually becomes more and more turbulent liftoff. So people who are interested in flame structure as a function of Reynolds number were happy with these kind of signals. He imaged, I think, up to down to about 40 diameters downstream, up to about 8 centimeters. This is a 2 millimeter jet up to about 80 millimeters. So that was what was possible. So, you know, people who are interested, there was nothing like this at that time. At that time, this was a real. Here's one of his axial cross sections, and here's the incredible detail, flame separation there. People who are interested in the structure of flames and how they behave with turbulence, Reynolds numbers, were really happy with this. This was 24,000. You see kind of a continuous flame. Now, this is the image in a plane, so you always have to ask what's happening in other planes and whether this is in the plane, but it probably has some out of plane behavior. Oh, here we go. So this is my student, Brian Kirby, professor at Cornell, and he's the one who agreed to take on this challenge of can we do PLIF in the infrared. So he used 2 micron excitation. This is a forced jet of CO2. Actually, it was a mixture of, in some cases, a mixture of CO and CO2. I think I'm going to show you the energy level diagram. He tuned his laser to 2 microns, which was absorbed by the CO2. Then he looked at the emission at 4.3. So you'll remember maybe that I showed different absorption bands of CO2, and there was some down around 2 microns, and then also some around 4.3. This is a false color display of a room temperature jet seeded with CO2 mixing in the ambient. So, you know, it shows that infrared PLIF can work. It's not easily, why would we do this? Well, because some of these species don't really, PLIF can't be done with single photon excitation of CO and CO2. Single photon can't be done. They don't absorb in an accessible region. So these are combustion products that we really care about, and also hydrocarbons. So advances in infrared lasers have made this possible. We had to buy some special infrared cameras. At that time, they were pretty unique. Microsecond resolved infrared cameras, indium and timonite cameras. They were pretty expensive at the time. When you're working, you know, it's hard to get a camera that works at 4 microns. Here's the energy level diagram. So here's where the spectroscopy is. We're ultimately going to see the emission out here. This is an energy level diagram for CO2. Here's the, and we're just looking at the nu 3 mode. That's the asymmetric stretch. Here's CO, and here's nitrogen. And I'm showing you these three because there's lots of possibilities here. Here's a case where we actually excited CO at 2.3 microns, which is the first overtone. So there's 2 nu. Nu is, we don't have to write the subscript 1 because there's only 1 mode for CO. This is a 2 nu quantum transition at 2.3 microns, first overtone. Once it's here, what can happen? It could emit at 4.7, that's the first overtone. Take us down to V equals 1. Or it could be collisionally quenched, or it could have a quenching, it could have a collision with nitrogen. So if you're up here, it turns out that this is not resonant with anything. So the dominant thing is that this will either emit or it'll undergo some sort of collisions with CO and then again emit. So this is basically A over Q, A over Q. This is the collisional rate. However, once you get to here, this level happens to be nearly resonant with nu 3. It's nearly resonant with the first level of nitrogen. And if there's a collision with nitrogen, the quantum of energy can go over to the nitrogen, after which there's no light. If it goes over to here, the subsequent emission will be at 4.3. And so we learned that if we excited CO at 2.3, this level, we could actually either look at CO2 CO fluorescence or CO2 fluorescence, which only occurs if there's a collisional transfer. So this was a way to try to get at molecular mixing. It was kind of a clever idea that you could use infrared and not look just at the tracer, which would be CO, but you could also look at emission from CO2. And then this is what I call the dark side. Once it goes over here, there's no emission. So whenever that process dominates, you diminish the laser signal. So that's like mixing with the dark side, mixing with the bright side. And then somebody gave us a CO2 laser. IBM gave us a CO2 laser. Now, this is the energy level diagram for CO2, which also explains how a CO2 laser typically works. So there's a lot of quantum numbers for, you'll remember that we have 4 modes for CO2. It's 3n minus 5 for a linear molecule. There's 4 modes, nu 1, nu 2, nu 3. Typical CO2 laser emits at 10.6. That actually corresponds to a transition between this excited state and this one. So CO2 laser works by virtue of somehow populating this state above its normal value so that it can emit down to this state. That's the energy level diagram for the 10.6 micron CO2 laser. And this is the energy, this is a reminder that we have the symmetric stretch. See, this is the new one, this is the new one mode, which is not infrared active, but it exists. Here's the bending modes over here. Here's the asymmetric stretch right here. So somehow you produce a population here, typically with the plasma. You electronically excite this state to above its population, and it wants to go here, emit light. It can emit at 4.3, but it wants to go over here, and we can get light at 10.6. So anyway, we had a, what does that mean? That means if you excite CO2 at 10.6, you can excite this level and make it go to here. When do you have population in this level? Only when it's hot. So we looked at this CO2 laser that they gave us, which emitted only at this wavelength, and we sent it through this hot jet. And where do we get fluorescence light? Only from this state, which is only there when it's hot. So this became a way to measure temperature of a hot CO2 jet. And I had this idea that we might use this idea to look at vertical takeoff and landing aircraft where they turn their engines and there's a lot of question of interaction of the hot gas with the ground. I thought we could look at this to look at the distribution of the engine exhaust. We never actually did that, but this was the idea that you have a cheap laser and you would look only for where is the hot gas. So here's an example of the success of using infrared PLIF. So we went on to study a simpler flame. We studied this called, it was a flame being studied by several people around the country. It's a co-flow jet. So this is a methane nitrogen fuel mixing and burning with surrounding air. So when it's steady, you would see some sort of a flame like this. This would be where the CO2 would be. If you did the CFD for this flow and you plotted this as a false color display of the CO2 concentration, you would see something like this. My friends at Yale were applying Raman diagnostics to obtain an image of CO2 in this steady flame to be compared with the CFD. We decided to do this with our infrared PLIF, and here's what we got with this 36-shot. This is a single-shot image. 36-shot average of this steady flame. This is what Yale got, but they had to use line illumination with 5,000 shots per row. So what does that mean? PLIF is a lot stronger than Raman. Well, fluorescence is stronger than Raman. You can decide whether you want to do a line or a point. You can decide what you want to do. This is just but the virtue of the Raman, in addition to CO2, they can do they could do nitrogen, they could do hydrogen. Raman is good for these homonuclear diatomics or the symmetric molecules. So I don't want to downplay Raman, but in this particular comparison, fluorescence is so much stronger. And they agree pretty good with these calculations. You know, our average here is looking pretty good. If you want to do a validation of CFD, it's hard to do an experiment with high enough signal-noise ratio to actually quantify the performance of the CFD. It's hard to get good enough signals in PLIF. You might do a line or something to be more. Okay, I've also been really interested in the SCRAMJETS, and this is another opportunity. So this was the HyperX concept from some years back. And inside this vehicle is this scramjet concept. Here's some sort of high-speed flight, say Machs greater than 6. Here's the supersonic inlet with some shocks bouncing around it. And then finally, there's a place where you're going to inject and burn fuel. In this scramjet, the rule of thumb is you have to mix and burn the fuel in 1 millisecond. So everything's going so fast. You have to mix and the question is, how do you do that? And of course, the question is, how do you verify that what you're doing? Well, you can measure thrust and so on. This would be a so-called, and in this concept, the scramjet, supersonic combustion, the combustion is taking place at supersonic Mach number greater than 1. So how do you test this on the ground? Well, really, it's even harder to test it in the air, but how do you test it on the ground? So you need some sort of non-intrusive diagnostic schemes. And so the way that this is pursued at high Mach numbers is what's called an impulse facility. So you use some sort of a tunnel. So you can, there's different ways of doing this, but the conventional way would be to get to Mach 6, you have to have really hot air, and you have to expand it. I showed you the example from NASA Langley. So you have to heat the air and compress the air and expand the air, have it flowing at high speed into the scramjet combustor. But a simpler way to do this for short flow times is to use a shock tube. So the shock tube produces a high-speed flow. Shock tunnel produces a high-speed flow. The shock wave is reflected, and then the gas is expanded in a nozzle. So for a period of a few milliseconds, you can have a slightly different variation of that is called an expansion tube. And in an expansion tube, you have a driver section, you have a driven section, and instead of having an end wall here and a nozzle, you have what's called an expansion section. There's a thin diaphragm here. Here's where the test gas is. Shock wave comes through, heats up this test gas,
and then it expands into a light gas, typically helium, and it can flow at high speed. So rather than reflect it, double the temperature, then expand it. You expand it immediately, and that avoids ever raising it to very high temperatures. So you avoid chemically changing the driven gas. So now here's our test section at the exit of this tube, and this is the gas is flowing out of this tube at some high velocity. This is going back in time. This might have been. This is before we had really high-speed cameras. We used something that was called an Imicon. This was probably around 1995. In any case, we didn't have the high-speed cameras then, so we had something called an Imicon, about a quarter of course, Imicons over. Okay, I'm getting my two stories mixed, sorry. We had an Imicon, which finally we could replace with an intensified CCD array. So we had two cameras. We had our original Imicon that cost $250,000, finally was replaced by an intensified CCD camera. And we're going to use this one to do Schlieren, and we're going to do this one to do OH. Originally, we just used this one, and I'm going to show you some results with that for PLIF a little later. We have some sort of a pulse laser over here, which is brought through this system, and we're going to examine this flow field. Here's the expansion tube concept. You've got a helium driver, so-called buffer. Here's our test gas. Here's the light gas. So what happens is this diaphragm breaks. It heats this gas, sets it in motion, but when it gets here, it expands into this unsteady expansion. Out of the tube, it comes and flows over some structure. So there was a project called the RAM Accelerator project. The Army had an idea that, and the Navy, that instead of, you might be able to shoot projectiles. The Army had the idea, the Navy was interested. You might be able to shoot projectiles from a ship better if instead of using solid propellant, you filled the barrel with combustible gas and use a light gas gun to inject the projectile into the barrel, and then as the projectile moved down the barrel, arrange for there to be combustion behind the projectile. So you would continuously accelerate, continuously push on the projectile along the length of the barrel using the continuously burning gases. That was the concept. They got it up to about 2.5 kilometers per second, I think, projectile speed. Because the downside was that it got too hot and the tips started to burn. But still, it was a concept. And the people were testing it by sending their shaped projectile down this tube. They were studying it by taking a Navy gun and then sending these projectiles in and into this big, heavy-walled, thick pipe. So how do you know what's going on inside? They measured pressure. My idea was, instead of moving the projectile, why not move the gas? So we parked our projectile here and brought the gas over the projectile so that we could do PLIF. That was my idea. So the virtue of the expansion tube is that you can accelerate combustible gas to high speeds without ever putting them at high temperatures and therefore keeping them from burning. When you do one of these accelerators, it's a little bit, the shock tube is not perfect, and so you have to do some test conditions. Here's some experiments where we use a blunted cylinder. So here's the blunted cylinder. Feed the flow with a little bit of nitric oxide, and here's the methane. The mixture for the RAM accelerator, called RAMAC, was methane. So if we leave out the oxygen here, we could just have the gas without the oxygen. And now this is the instantaneous image with PLIF that we acquired. And these are false color displays of the NO signal. So there's the bow shock, and there's the gas. And those of you who are gas dynamicists will understand this. There's something about the standoff distance and the angles that tells you about the flow. If you do a wedge, if you have gas dynamics, you'll know that the angle of this wedge and the angle of the shock wave is determined by the Mach number and gamma. And this is how people calibrate these tunnels. They measure this angle and say, gee, I know this angle, and I measure this angle, and I know gamma. I've just determined the Mach number better than I can calculate it. That's a common trick. So we could do this. This would be like Mach 7 in this case. And we could have a free stream temperature of about 280 that simulates maybe atmospheric air. So then we got interested in doing this. I'm kind of going back and forth on projects here. This is the RAM Accelerator project. And now we're going to do OH imaging. So here's the spherical cylinder in the case where there's oxygen in the flow. And now the people who've had combustion course would say, well, what's the CJ speed? These images all depend upon the CJ speed. If the free stream velocity is greater than the Chapman-Jaquet speed, you'll get this nice stable picture. There's the shock wave revealed by Schlieren, and here's the OH revealed by PLIF. And you could model this and then ask if you can model this flow field. Here's a case now where the free stream velocity is quite a bit higher, 1.32. And anyway, you get some beautiful pictures here of supersonic combustible flow over a particular body where you see the shock angle. So the computational people love this. This was the way they could test their models. Now what happens? If you reduce that free stream velocity to be less than the CJ speed, that means that the detonation, it wants to detonate. And when that happens, you get this burst through the shock wave. So this gas in here is such that it wants to detonate. It wants to push forward. And when you drop that free stream velocity below the CJ speed, you get these really interesting structures. This was the one that, this was Professor Matsuo in Japan, wanted this test case to test for CFD. Now I'm going back to the scramjet problem. So now the scramjet problem is high Mach number flow over a flat plate with injected fuel, in our case, hydrogen. And so the gas dynamics people know there's a Mach disk here, recirculation zone. And the question is, over what range does it burn? Over what range does it burn? You're interested in these jet shear layer vortices. Depending upon the momentum of the jet, usually it's the momentum of the jet divided by the effective momentum of the cross stream determines how far it penetrates. Okay, now we're back to, we had to use our, only high-speed camera we had at that time was this old camera. But we could take pictures at a high frame rate, microsecond exposure. So now what we're looking at is the Schlieren images. What was I expecting to see? I was expecting to see a shock wave that was fixed in space, like you see in a textbook, like this. But when you do this at high speed, you find out that these flows are not as steady as you think because of the intermittent structure of this mixing here. This is a burning mixing jet. There's the instantaneous structure revealed by Schlieren that causes this wave to not look like the textbook pictures. So the virtue of this high-speed camera in this cross-flow problem relevant to the scramjet was to reveal that these flows are not really steady. Now we look at some single-shot images of the OH in this combustion flow. So here's the hydrogen coming in. Here's the cross stream at 1300 Kelvin and 2.3 kilometers per second, which corresponds to Mach 3.4 in air. And in this case, we've done my trick, and we've said that this signal is proportional to the mole fraction of OH times some function of T. If you look at this, you see, you can at least reveal the structure. You can see the penetration distance. You can see that it burns. If you look close, and here's a better picture. This is a little bit higher, lower temperature, but it's in oxygen. You can see the recirculation zone. You can see, here's the jet. This is what the CFD people wanted to see to do their code validation. We studied the influence of the jet momentum ratio. The idea was that this recirculation zone got bigger and bigger and served to stabilize this. We came back to this a few years later, and we began looking at this again, and see that the burning was taking place on this is OH. So we can see burning on the surface. We can see this continuous structure here. The postdoc, now Professor Gamba at Michigan, translated the plane of observation, but we only get one shot per run, so you have to repeat this run over and over and over, and he would do this at very variable. Y is the distance off the surface. For far from the surface, all the way down to right at the surface. You could see instead of just having this cross-sectional view, we can see where is it burning and how's it mixing and so on. So, and he has a plot here of, I don't think it's going to play the movie. I don't think the movie's going to play. But we could do these cross-sectional planes in all different orientations and study this. Okay, looks like it may play. So this took a lot of work. We had to repeat these experiments over and over and over and over. But he could build up a 3D picture of this thing. This is what the CFD people wanted. Where does it burn? So here's a case where we don't have absolute values of OH, but we can at least tell you where the OH is. I had another student who was interested in measuring temperature, and he was going to use the temperature ratio using nitric oxide. Now it took 2 lasers, 2 cameras, lots of electronics, and the goal was to look at the temperature in this flow field. Supersonic air, hydrogen jet is kind of the same problem. Here's the backward-facing step, it's called. I think these were the world's first instantaneous temperature images in a flow like this. So nitric oxide deceived into the hydrogen jet, and these are false color displays. So cold is blue and yellow is hot. You could put NO tracer here and here, or you can just put it in the jet. So now you can see the jet is cold here, hot along the edge. So you can see where this flow, you can see the recirculation zone, you can see the barrel shock. So what are we seeing? Now this is a case where we looked at NO, and he used his second laser to measure OH. So you can see that downstream about 10 diameters, it starts burning in the boundary layer. So this is, and he has some images down, cross-stream, now cross-stream, downstream, and you can see the NO is mixed everywhere, but the OH is burning in like a ring. Okay, so how have I done? So what I tried to show you is the power of planar laser-induced fluorescence for sometimes qualitative imaging. It's qualitative, really. It's quantitative spatially and temporally, and qualitative in terms of the mixture mole fraction, or the mole fraction. We can get to temperature. And so it's a really, you learn so much about the flow field by looking at images. It may be different than you expected. It may be similar to what you expected. So you learn something from the structure of the flow field alone. I think I must have sailed through that in record time. Okay, in the next lecture, we're going to now look at what we can do with flow tracers. I've been showing you small molecules, NO, OH. Now we're going to go to look at some flow tracers that you can use at room temperature. Acetone in particular, 3-pentanone. We'll do this kind of at room temperature, then we'll do IC engines, talk about high-speed imaging, toluene PLIF for temperature. We'll end up on that. So we're down to we'll be down to the last lecture. So it's the one where we're doing PLIF, tracers, sometimes quantitative, sometimes only qualitative, but a real powerful diagnostic tool. So the title of this lecture series is Quantitative Diagnostics. The whole idea is that fluorescence is really just absorption with a twist. By going to fluorescence, you can get images. The absorption is truly quantitative. The fluorescence is nearly quantitative. It's spatially quantitative, temporally quantitative, but it's hard to get it to be quantitative for species concentration. But we can make it quantitative for temperature. We can make it quantitative. I didn't show you any, but we've also done images of velocity. You can image velocity from the Doppler shift. There are lots of tricks that have been developed over the 30 or 40 years. Approaching 40 years, older than anybody here, probably except me. Okay, any questions? So I think the key message is, if you want spatial resolution, you go to fluorescence, or you try to go to fluorescence or PLIF, LIF or PLIF. If you have a relatively uniform line of sight, absorption is the way to go. It's quantitative. It's always down to, you have to understand the spectroscopy to know what wavelength to use for your laser. So fluorescence imaging still rests on the same understanding of line positions and line strengths, and line shapes. If the course, over time, everything gets better and better because the cameras get better. The cameras have really improved over went from really difficult cameras to now you can buy a camera that goes, 1,000 frames a second, 200 by 300 pixel size. Cameras have really changed. Computers have really changed. The lasers have gradually changed. Gradually have gotten maybe faster, more energy. And of course, these now have become more routine tools in laboratories around the world. But these PLIF systems, or Raman systems, tend to be pretty big, awkward, mostly confined to a laboratory, or it could be an industrial research laboratory, but you're not carrying them around in a suitcase. Our diolaser systems can go in a suitcase. Depends on what you're trying to accomplish. But still, they all rest on absorption. So that's the rationale for why I focus on these subjects for these lectures. Okay, so we're at 10:50. If we start at, say, 5 after 11, we'll finish it by 12 or so. Okay? All right, see you.